Hello, today I would like to talk about stability in discrete time control systems, and we will approach the context of stability from the perspective of pulse transfer functions. Okay, so given a closed-loop transfer function, let's call it T of C. So we know that the pulse mainly determines the stability of the dynamical system if it's a full course and a linear time invariant system. Okay, so let's draw a z-plane. Okay, and let's talk about in one conditions, location of the poles will determine the stability behavior. Okay, so we know that the unit circle defines the main region of stability. Okay, so first of all, let's start with the stable case. If all of the poles, okay, of a transfer function are located inside of the unit circle, all poles inside the unit circle, okay, which means that the magnitude of the poles are all less than 1. We know that the system is both asymptotically and bistable. Okay, so bistable stability is technically bounded input, bounded output, which means that for any kind of bounded input applied to the system, the output will be also bounded. Okay, so I think you remember the proofs and details from 301 classes, so I will not go into these details, but it's kind of easy because when we have a pole P, technically it has a effect on the transients and the output in terms of P to the power K, and of course if the magnitude of P is less than 1, it's stable. If magnitude of P is higher than 1, it will go to infinity. If P is equal to 1, we know that it will just go to constants. It seems to be stable, but it's not. Okay, so which is the next topic? Okay, so for a full stable condition in terms of both asymptotic and bipole stability, this is the condition. Okay, so the next step is, okay, so let's talk about this. If there exists a simple non-repeated roots on the unit circle, okay, but all of the other roots poles are inside the unit circles. For example, in this condition, let's assume that we have a pole here, we have 2 poles here or something like that, okay, then we call it marginally or critically stable, okay, so for this kind of systems. But we know that marginal and critically stable systems are bipole unstable. Okay, and the reason is simple. Okay, let's assume that we have a pole at the z is equal to 1 point. If we give the impulse, it will be constant, okay, which is technically related to asymptotic stability. So it's not asymptotically stable, but it's not technically unstable from this sense. But we know that if we apply a step input for a system which has a pole at z is equal to 1, because of this coupling, the output will go to infinity. Okay, so it's kind of easy to see that for bipole stability, all of the pole has to be inside the unit circle. Okay, so we can call it a marginally stable system. That's fine, but because we talk about something else, the notion is different, but it's technically bipole unstable. Okay, the next condition is, okay, so if there's a repeated pole, for example, on the unit circle, then it becomes automatically unstable in all notions, both asymptotically unstable, it's not marginally stable, and bipole unstable. And of course, if there exists a pole outside at least one pole of the unit circle, then this system is automatically unstable because of the technique. Any impulse or any input will go to infinity as time goes to infinity. Okay, so this is the basic idea. And for continuous time dynamical systems, if you remember, we use a method called root Hurwitz. Okay. In the root Hurwitz, the whole idea is given a transfer function, okay, we have denominator, okay, and by checking some conditions, we try to test if all of the poles are located in the open left half plane or not. This is the whole idea in root stability analysis. And later we learned that we can modify this method a little bit to test if all of the poles, for example, located in open left half plane, but for example, we can have some sort of threshold in terms of settling time by rechanging the poles and other kind of details. Okay, I really recommend you to reread your lecture notes in root orbit stability. My lecture notes in feedback control systems are also in GitHub. You can look at that, and you will need root orbit stability test in the second stability metric. I will talk about most probably in the next video. Okay, so in discrete time systems, instead of root orbits, we have a different test. It's called jury stability test. Stability. Okay, so the main difference between jury and root orbits is application of root orbits is okay. It is kind of easy, but it's not that easy. But jury stability test, especially for higher order systems, is a little bit more complicated. Okay, in my opinion, it's kind of impossible to memorize jury stability test. I don't memorize that. For that reason, I'm making all of my exams open material. But it's important you to understand the algorithm and details, because in a midterm environment, you should be careful such that you won't do any mistakes. Okay, for this reason, instead of just going into the algorithmic test of a general jury stability test, I will start from special cases, give some intuition, okay, and later we will just give the reasoning for a general nth order system. Okay, so let's start with that. We have a d of z. Okay, d of z is the denumerator of the transfer function, and it can have a form like this. Okay, z to the power n, a1, z to the power n minus 1. It goes like this, a minus 1, z plus a n. Without loss of generality, we can assume that a0 is greater than 0. It's just positive. Okay, we can also assume that a0 is equal to 1, but that's fine. So it's not a big deal. Okay, so let's start a first order dynamical system. First order, which is the most trivial and easy one. Okay, n is equal to 1, and d of z can be written in simply this form. Okay, plus a1. This is super easy. Okay, we know that pole of the system is equal to a1 divided by a0. Okay, so we know that magnitude of p should be less than 1. We know that a0 is already greater than 0. So for a bibostable stable condition, bibostable stability, we need to satisfy that a1, magnitude of a1 should be less than a0. Okay, so it's very easy to test stability for a first order system, and this is technically the jury stability test. We are doing it here, which is kind of obvious and not complicated. Okay, good. So let's go to second order case. Okay, d of z, okay, is equal to a0 z to power square plus a1z plus a2. Okay, so in order to give the intuition, I assume that my poles are distinct and real. Okay, so it can be like double pole, it's fine, but I kind of ignore the complex conjugate part, because complex conjugate part will not affect the results. Okay, but it's easier to see the details when we have two real roots. Okay, so if we have two real roots, okay, we can write it in this form, right? Okay, let's say that it is equal to, let's say a. Okay, I'll just give an idea. Z plus p1, z plus p2. Okay, and technically this is a0. You know that, right? This is a0. Okay, technically this is exactly a0. Okay, this is equal to a0 z squared plus p1 plus p2 z plus p1 times p2. This is equal to, okay, a0 z squared plus a0 p1 plus p2 z plus, okay, the a0 times p1 times p2. Okay, that's it. Okay, so what is that? Okay, so we have a constant p1 times p2. Okay, so first of all, if p1 is less than 1 and if p2 is less than 1, it's kind of easy to see that, okay, a0 p1 times p2, okay, should be less than a0, right? Okay, and of course, let's call the magnitude, and this is kind of easy to see that if both poles are inside unit circle, we have this condition. What is a0 p1 p2 magnitude? Is simply okay, we can deduce that A2 should be less than A0. Okay, so this is our first condition. Okay, and it's easy to verify that this is also true when your poles are complex conjugate. Okay, which means that your last coefficient in polynomial A2, its magnitude should be less than A0. This is condition 1, but it's not enough. Okay, and I will talk about that later. Okay, so we already come up with a constraint for pivot stability. Okay, now I will draw something else. I know that okay, so A2 should be less than A0. I have P1, I have P2. Okay, so what is D of Z? Let's rewrite again. A0, Z plus P1. No, it's not plus, it's not a big deal. Okay, so let's write it. Z minus P1, Z minus P2. Okay, good. Okay, so what I want is, since all of my poles are real for now, for this intuitive example, I know that they're on the real axis, and it doesn't have to be on the real axis. Okay, so what I want is, I want my poles to be inside the unit circle. So what I want is, I don't want any pole here, and I don't want any pole here, and I know that I have exactly 2 poles. Okay, good. So I want this. Okay, so let's analyze different conditions and try to have an idea about the stability. Okay, so if my poles are all inside the unit circle, I can compute 2 different quantities. Okay, which is D1, okay, and I can compute D minus 1. And what I will do is, I will just look at their signs. Sign. Okay. Sign. Okay. Sign D1. So if my poles are inside the unit circle, okay, so what is D1? D1 is equal to A0, Z minus P1, Z minus P2. So I'm looking at this line. So from the first pole, it will become negative. From the second pole, it will be negative, and this sign will be positive, so it will be equal to 1. That's great. Okay. So now in the second case, D minus 1, so I'm trying to look at where the poles are located with respect to Z is equal to minus 1. Z is equal to minus 1. Okay, if my poles are both on the right hand side of this line, okay, first pole will give a positive, and second pole will give a positive sign. It will be equal to 1. Okay, so it means that if my poles are all stable, D1 should be positive, D minus 1 should be positive, or sign of D1 and D minus 1 should be both positive, or 1. Okay, that's good. So now let's look at a different case. Okay, so let's draw it again. And let's assume that I have a pole here. So one stable, one unstable pole. Okay, this is good. So we know that this is stable because we constructed a stable system. Okay, now let's look at D1. Okay, D1. Okay, from the first pole is on the negative side or on the left hand side. So we will have a minus 1. Okay, we are looking at the side. This will give a minus 1. This will be positive. 1 minus 1 times 1 is equal to minus 1. So now we have a sign, it's minus 1. So if we look at from this perspective, since both of the poles in the right hand side, sine of D minus 1 is equal to 1. Okay, so what happened is, since I have unstable pole, D1 end up being negative. And I know that this is unstable. Okay, this is unstable, this is stable. Okay, so let's change it again. Okay, this is good. This is nice. Let's see that I have a pole here. That's also good, no problem with that. Okay, so I have a stable and unstable pole. Let's look at D1, and it is sine. Okay, so since my both poles in the left hand side of this Z is equal to 1 line, so they will be both negative and the sign will be is equal to 1. Okay, but if I look at the perspective of z is equal to -1 line, sine d minus 1 will be equal to -1 times 1, and it will be is equal to -1. Okay, so stable case, d1 and d minus 1 is equal to 1. Unstable case, it's -1. Unstable case, it's -1. Okay, so we are just getting somewhere else. Okay, so now let's look at something else. And it's assumed that both poles are negative. Okay, both poles are negative here. So if you look at that, both d1 and d minus 1 will be equal to 1. Okay, so is it, but you know that it's unstable. But if your both poles are here, we know that their multiplication will be larger than 1 and it will fail the first condition here. So these conditions are complementary to the first condition. Okay, now if we summarize the result, it's very simple for second order systems. For d of c, which has the form of a0 z to power 2 plus a1 z plus a0, and if a0 is larger than 0, okay, it's an assumption, for a discrete time system is stable if and only if it's technically we satisfy all of these conditions. A2 is less than A0, D1 is greater than 0, D minus 1 is greater than 0. That's it. Okay. So if we have a pole on the unit circle, it's kind of easy to see that these conditions will be equal. Okay, so if D1 is greater than 0, for example, it's stable. If D1 ends up being less than 0, it's unstable. If D1 is equal to 0, but everything is satisfied, it means that we have a pole on the unit circle. Most probably it's equal to 0 to 1 or it's equal to 0 to -1. That's it. Okay, so for second order discrete time dynamical system, actual testing stability is relatively easy. When we go to third order and in higher order, it will become a little bit more complicated. And let's try to do that. Okay, let's try to do that. Okay, so for a third order system, okay, d of c, okay, a0 d to power q plus a1 z squared plus a2 z plus a3. Okay, so first of all, I couldn't find any nice intuitive way of explaining jury stable test starting from third order case. Okay, now we just use the technique because the technique deeply rooted in linear algebra and it requires a couple of different proofs to prove the whole test. So we will just use as an application. So what we need to do is we need to construct a jury stable test. Okay, for a third order system, it's kind of easy. Okay, this is rough. Okay, we write the coefficients here, z1, c1, z2, z3. Okay, so when writing row 1, first row, we flip the order of the coefficients and start from a3, a2, a1, a0. Okay, in the second row, we just flip the order again, start from a0, a1, a2, and a3. In the third row, what we do is we compute 3 different coefficients, b3, no, b, okay, sorry for that, b3, no, it's b2, b2, b1, and b0, and that's it. Okay, so we only need to compute these coefficients. We already know a's, we only need to compute the b2, b1, b0. Technically, b2 and b0 enough. We don't need to compute b1, but this is all there. So how we compute, for example, b0? b0 is very simple. b0 is the determinant of a3, a2, a0, a1. Okay, so from graphically or from table wise, what we do is we take these two, first column of the A matrix, let's say matrix, and then we take the second one. We form a matrix using this column and this column here and compute the determinant. To compute B1, we do a similar thing, A3 and A0. As you can see, these first columns are equal. But the second case, in the second column, we change it to A1 and A2, take the determinant. So what we do is here, so we already used the first column. Now we skip the second column and go to third column. to compute B1. Okay, take the determinant. And B2 is equal to, let's change it again, A3 and A0. As you can see, we are still using the first column. And what we have left is the only last column, which is A0, A3. Take the determinant and compute the B2. Okay, so this is the jury stability table. Okay, once you compute the jury stability table, now you can construct the jury stability test. Okay, so what we do is, let's change the computations. Let's clean that, and I will state all of the conditions. Okay, that's good. Everything is nice. Okay, so in order for a third order system to be stable, once you construct the jury stability table, you need to satisfy this condition. Magnitude of A3 should be less than A0, which means that magnitude of the last coefficient should be less than the first coefficient. Of course, we know the fact that A0 is higher than 0. Okay, that's good. D1 should be larger than 0. D minus 1 times minus 1, I will talk about this, should be larger than 0, or we can say that D minus 1 should be less than 0. Actually, the motivation of this coming from the exact motivation for the second order systems. And we have one more condition, which is magnitude of or absolute value of B0 should be larger than absolute value of B0. Okay, so in general, I really think that remembering these details is hard. Okay, but what you should do is just put your GeoTable notes, because my notes are also open source. Solve a couple of examples, get some practice, and in the midterm, just bring your table or details next to you, and you can just solve the solutions or the problems looking at the notes. That's fine. Okay, because I think it's really, really hard to remember this. Okay, so the motivation behind the first three conditions is clear. I already provided you for a special case, but the remaining motivations is more complicated and it's kind of hard to understand, but this is the whole idea. Okay, so in midterms, I only ask second order or third order systems. So this will be enough for the midterm. But of course, in the mini projects or maybe in other kind of practical cases, I may force you and challenge you for higher order systems, but I promise you that in the midterm, you will apply jury stability test or other couple of the different tests for only second order or a third order system. Okay, so in the next video, I will talk about a general GeoTable, okay, because it's a lecture, I still need to talk about that, and we will see how complicated it can get for higher order systems. We will solve examples, and later I will talk about a bilinear transformation and Routh-Hurwitz based stability test.